crossing. Answer your question?
Thank you, Professor Lewis. Our next speaker is Professor Kourou. He's going to talk about CO2 capture.
So, good morning. So I will be presenting about CO2 capture, and this work is mainly done by Afroditi Kourou and one of my associate professors, Professor Yu Yang. We do a lot of work in Ghent on CO2 capture, but this has been evolved starting from a sort of special reactor, a gas liquid vortex reactor. And we have been developing this technology for over a decade in my group. And step by step, we are moving indeed from something that has been developed in a lab to a spin-off to companies. And also my wife is very happy that I have a spin-off that makes a lot of money. So just to support that, I can only acknowledge that. So carbon capture and utilization, I think it's clear for everybody. But if you look at all the policy predictions, then one of the major efforts that people see that will be needed is CO2 capture to do something on relatively short notice. And because it's a technology which is ready, we have industrially employed plants. It requires a bit of infrastructure, but not too much. Companies see opportunities in that. Basically, they see opportunities to make money, in particular oil companies. However, there are some challenges remaining. So the energy requirement is one of them, and the cost is another point. So you see huge variety in the cost of CO2 capture. And this is depending on the technology, but also the concentration of CO2, the amines that you used or something, or and so on. Of course, you have different types of technologies. You have absorption-based, you have cryogenic, membranes, and so on. But people, for point sources, mostly look at chemical absorption as being the dominating technology. Yeah. How does that work? Well, you start with flue gases here on the left. You have some cleanup, and then they are sent to an absorption tower. Yeah. In this absorption tower, we have an amine typically. We have a solvent in water that is basically trapping the CO2. And this means that you end up in the end with a concentrated amine, which needs to be stripped. So here the CO2 needs to be removed, and that's done via heat primarily. So the big energy consumer here is this reboiler. Yeah? And in the end, if you look at the OPEX, then all the OPEX is mostly determined by this part. So you see 70 to 80% of the OPEX is this reboiler duty. Yeah? So if you can bring this reboiler duty down, then everything else makes sense. Yeah? On the other hand, from a CapEx point of view, these absorption and desorption towers are huge. Yeah. So it's like with everything in the chemical industry, you pay for steel. The larger it is, the more steel that you need, the higher the cost. Yeah. So if we can make these things smaller, the cost will go down. Yeah. And that's in the end what we try to do in Ghent. And we call that with a fancy word, process intensification, smaller and more efficient. Yeah. So there are a lot of definitions of process intensification, but I like this one of Professor Stankovic. He's one of the pioneers in process intensification. So it's a chemical engineering development that leads to a substantially smaller, cleaner, and more energy efficient technologies. Yeah. In the end, doing less with more. See that you're not awake, it's more with less. Okay, good morning. Yeah. So here you see our vortex technology. This is the first generation. It looks a bit like an octopus. And it was originally developed for gas-solid kind of systems. This is cold flow, just looking at the flow. Here you can actually heat things. This is for reactive purposes. We use it for biomass conversion. We use it for catalytic processes. So with the solid, you really see the solid particles rotating very quickly because you have small openings in the side. And here comes the gas in a tangential way, and this basically drives the rotation. Yeah. And so you can see here, so you see here the gas flowing, and it's basically divided over these slits that you see here. And in this way, you get this rotational movement, and then everything leaves over the exit. So what is the main feature is that you get an intensification of heat and mass transfer. And the good thing is also you have no mechanical rotation. Yeah? This is also from a cost point of view, makes it easier, but also it makes it also more robust. And this is what we mean with process intensification. So 7 years ago, we moved, after a talk with Heinz Pitch, he said, well, actually this device is interesting, but why don't you use it for CO2 capture? I said, yeah, maybe that's indeed, it's a good idea. And we did our first experiments, and we made what we call the gas-liquid vortex reactor. So again, tangential inlet of the gas. So this is the red arrows. The liquid is entered in the center, is divided. And what you see is you really, so these are camera pictures, get a very large interfacial area. Yeah? So very high energy dissipation and very good momentum transfer. And this is, of course, excellent for absorption, but also for desorption. Yeah. And so over the years, we have developed this thing further. Yeah? So we see a very high turbulent flow, intensification of the mass transfer. And again, we can keep this mechanical rotation, and we can avoid that. And we have optimized the design based on CFD. So we did computational fluid dynamic studies to optimize the initial structure, and we have really very small equipment. But again, the crucial step is not so much the absorption, but it's really the desorption. Yeah? And so we have here our classical desorber, and here we have the vortex desorber. Yeah? So we have here the solvent, the rich solvent which is entering. We have the steam that is needed for stripping the CO2. We have a gas lipid separator. Captured CO2 goes to the right, and here we have the lean solvent. Yeah. So again, what we want to prove is really this reduced energy requirements, because this will reduce the OpEx. Yeah. So we studied this experimentally. It's nice to study things computationally. So what we did is we have here our solvent, our rich solvent. It's fat. We have a coriolis flow meter. We 3D printed a gas liquid vortex reactor. We put it in an environment. We put detectors, 2 types of detectors to double check our results. Liquid samplers, but also infrared gas analyzers. So really to be sure that we can measure the CO2 concentration at the outlet properly. And then, of course, we have our lean solvent, which is leaving as well. Yeah. So here you see it in real practice. You see how small this equipment actually is. So this is really the gas liquid vortex reactor. It's very small. These are cyclones, preheaters, and so on. So everything else is a lot higher than this vortex reactor. Yeah. So very compact. And this is again, shows already the nice capex reduction potential. In this small unit, we use a gas flow rate of 15 to 25 normal cubic meter per hour, and a liquid flow rate 10 to 40 kilograms per hour. So this is a device like this, and you have this kind of high flow rate. So from that point of view, you really show the intensification potential. Yeah. We calculated energy input. Another performance index is, of course, our regeneration efficiency. So this is in effect how much CO2 comes out versus how much CO2 we actually put into the liquid. So we want to, of course, ideally have 100% of the CO2, which is in the rich amine, leaving. This is, of course, not always the case. It of course depends on the design. Yeah. So here you see the results of these liquids and gas flow rates and the same geometry. So the geometry is always kept the same. And you see that we see a substantial influence of this gas and liquid flow rates. Yeah. We see that for constant gas flow rate, the regeneration efficiency increases with decreasing liquid flow rate. Yeah. Energy rate would remain the same. The liquid hold-up increases, so it's obvious that this becomes better. Yeah. At best, you have a high regeneration efficiency of more than 75%. So this is a very nice, decent value. Also considering that we did not optimize the desorber design. We just used something that we had available. So this shows potential. If you look at the 3 different CO2 loadings that we studied, so these are the 3 different loadings, then of course, if you have a higher initial loading, you have a higher driving force, and of course, we have a higher release rate. So we go up in this direction. At a high liquid flow rate, so this direction, so we have that favors CO2 release rate, while a low liquid flow rate favors the regeneration efficiency. So we have a bit of an optimization target that we can play with. But then we also compared our technology then to the current state of the art. So we have the classical absorbers, so these are here. And then we have the rotating packed bags, which are known to be a bit superior. But if you compare it to a CO2 release rate, then we are really almost an order of magnitude better than rotating packed bags. And so this is really a very advanced performance. And of course, then you get interest from companies and so on. So this is where we are today. A lot of interest from companies. And now we have to demonstrate this combination of this absorber and desorber on a larger scale. So at least showing that it's also possible at the higher flow rates. But it doesn't stop there. What you can also do is not so much on this absorber desorber. You can also play with the process scheme. So a classical process scheme of an absorber desorber has this heat exchanger in the middle, have this reboiler and so on. You can also do clever things here to reduce capex, opex, but in the end, to reduce this reboiler duty. And we did a whole study, looked at capex, opex, and PV for a classical absorber-desorber combination with MIA, because MIA is typically the solvent that is studied best. And we looked at a whole range of modifications. So the first one is this one, so intercooled absorber. Of course, it costs a bit of capex, but the solvent is partially withdrawn and generated ectothermic heat is extracted. This results in increased CO2 load, lower solvent recirculation, lower reboiler duty. So this is always our objective. This is the first thing we studied. The second thing we studied is rich solvent splitting. So we split the solvent partially, send it to the heat exchanger, but also to the top. So the cold stream is fed to the top, reduced reboiler duty. The third one that we studied is lean vapor compression. So we have a lean vapor, solvent is flashed, flash here, compressed, reduced reboiler duty. The fourth one, rich vapor compression. Rich solvent is in this case flashed, and the flash vapor is compressed, reduced reboiler duty. So then the last one, stripper overhead compression. So stripper overhead compression here. Desorber's top is compressed, stream is partially condensed, with less condensing energy, and reduce reboiler duty. So all these things are possible. They all require a bit of investment. But what you can see is that they have a substantial influence on reboiler condenser duty. So you see, this is the base case. And you see that especially this lean vapor compression, can result in 21% reduction of reboiler duty. And you see that also intercooled absorbing, that basically this gives 9%. You also see that sometimes, of course, this will result in a bit of electricity. That's why you also have to look at OPEX and CAPEX. You see that in the end, for the LVC, this even results still in a lower OPEX. Nevertheless, there's a CAPEX cost for this. So you see that all these different changes in the process can really help to substantially decrease the OPEX. What is the nice thing is that they are additive. You can combine them. So, and then the result becomes even a lot better. We will publish the results soon, but that's why I cannot really share them fully. But it's really impressive what you can do with this combination. So these three combination has really superior performance. And this is actually what we're going to demonstrate. So we're building now a unit. Investment is around 2 million euro. So with the vortex absorber, vortex desorber, and then with solvent splitting, with vapor compression, and lean vapor compression. And based on our calculations, we end up with 1.7 gigajoule per ton of CO2 energy consumption. If you compare to the best published and proven technology from BASF, that's 2.5. So we basically are 30 or 40% lower than that. So that's pretty enormous. Of course, it also depends on the solvent, so we will test plenty of solvents. Numerous companies are involved, ExxonMobil, Dow, and so on, because this can be really a major bit. And we will not go for a small scale unit, we really go for a kiloton per day unit, also to show scalability. And we will even demonstrate it on site at ArcelorMittal, which is one of the biggest steel producers in the world, to couple it to their chimneys. From a techno-economic point of view, you can just see from a CAPEX point of view, and these are not our numbers, this is the Flemish Institute for Technology and Innovation. They see that there's a factor 3 difference in CAPEX. So factor 3 reduction in CAPEX, and also substantial reduction in OPEX. And this really shows the very nice potential of this technology. Voila. So vortex absorber desorber, I think, has enormous potential for CO2 capture. This thermal integration allows to further decrease the reboiler duty. That's essential for the OPEX, but demonstration is needed to really assess the potential of this at higher tier. Well, thank you for your attention, and of course, I thank ERC and many others for sponsoring. Thank you.
Thank you for a great talk. So while the next speaker comes up, we have time for one or two questions. Any questions from the audience?
Thank you for your presentation. Is forming the challenge forming you are the next. Yes, you are the next.
So we have done tests with different amines.
Have you copy your PowerPoint?
Yeah, the morning I give it to you.
So,
Yes, I can have
and
it.
you notice kind of curve, but
Which is
media, the anti